Hi, this is part 2 of module 6. In part 1, we have talked about multilayer perceptron and we have stopped at the derivation of the backpropagation algorithm. The objective of the backpropagation algorithm is simply to adjust the weights and biases of our neural network model. And as we have seen earlier, it involves two phases: the derivation of the algorithm. One is the forward pass and the other one is the backward pass. We will see what are these shortly. So this is the derivation of the equations to adapt the weights and biases. Even when we are actually adapting or adjusting the weights and biases, there will be still two phases: forward pass and backward pass. In forward pass, we'll be computing the output of our neural network model given the inputs, and in backward pass is where we actually adapt the weights and biases. And we have assumed our derivation to be based on this model. Capital I, capital J, and capital K can be any value. The derivation would still hold. However, our model that we have assumed has only one hidden layer. And these are the various symbols that we have to take note: inputs, output. These are the bias weights. These are these are the hidden bias weights. These are the output bias weights. These are hidden weights, and these are output weights. And we have assumed that the input neurons implement the linear activation function. The hidden and output neurons assume the logistic activation function. The output of each neuron will be produced by the summation of input signals passed through the activation function. So in forward pass, the output of the artificial neural network is given by this. So if you remember, this is the logistic activation function with C equals to 1. So in this derivation, we assume the C to be 1. And as you can see, this is the input to our output neuron here, which is basically the summation of all these signals. So 1 multiplied BO1 plus YH1 multiplied WO11 plus YH2 multiplied WO12 plus YH3 multiplied WO13. So in general, you can write SOK to be as an equation 2. So from here we can see that we have to compute YHJ, which is the output of hidden neuron, and it's again given by the output of our logistic function, and this takes in the input to our hidden neurons, SHJ, which is again the summation of various signals. So there we go. This is forward pass. Is simply the computation of the output of our artificial neural network model. Of course, in order to compute the output, you have to compute the inputs to our output neuron, the outputs of our hidden neurons, and the inputs of our hidden neurons. So 4 equations to compute the output of our artificial neural network model. Now backward pass. The objective, once again, of the backpropagation algorithm is to find the next values of the adaptation weights, delta or the changes of hidden weights, the changes of the hidden biases, the changes of our output weight, and the changes of our output bias. And the weights and biases are adapted at each iteration, capital T, as follows. New hidden weight equals to old hidden weight plus the current changes in the hidden weight. Old hidden bias equals to, new hidden bias equals to old hidden bias plus the current change in the hidden bias. New output weight equals to old output weight plus the current change in output weight. New output bias plus old output bias plus new change in output bias. So we have to derive these four terms: delta WHJI, delta BHJ, delta WOKJ, and delta BOK. The backpropagation algorithm repeatedly adjusts the weights of the connections in the neural network so as to minimize a measure of the difference between the artificial neural network output, which is YOK for k equals to 1 up to capital K, and the desired output YDK for k equals to 1 up to capital K. So this is a measure of difference is basically the error. So we have to define what is the equation of error in the first place. So the aim of the backpropagation algorithm is to find a set of weights and biases that ensure that for each input vector, the output vector produced by the neural network is the same as or sufficiently close to the desired output vector. This is carried out by minimizing the total error E, which is given by this. So half multiply the summation of desired output minus the output of our neural network squared. So the minimization of this error is carried out by a method called gradient descent. So basically, the backpropagation algorithm will always adjust the weights in the direction such that this error is minimized, or at least it tries to minimize it. So to minimize error by gradient descent, it is necessary to compute the partial derivative of error with respect to each weight in the network. For the adaptation of output weights in equation 6, where is equation 6? This is equation 6. We have delta OKJ, so we are deriving this now, equals to minus eta partial derivative of error with respect to output weight plus alpha delta WOKJ of the previous iteration. So this is the current iteration, this is the previous iteration. And we can break down this term using the chain rule as del E del Y del S multiplied del S del W. So eta is the learning rate. So it determines how fast our training will be. Alpha is a constant that determines the effect of past weight changes on the current direction of movement in weight space. So it has been shown that having a non-zero alpha would enable our algorithm to escape or to avoid the local minima. So our objective is always to go in the direction of or reach the global minimum. But often our algorithm would be stuck in local minimum. So from equation 7, from this equation, remember we want to derive del E del Y OK. So we have E, we have Y OK. What is the derivative or partial derivative of error with respect to Y OK? So it is given by minus desired output minus our output. Because we are doing all this for a particular K and particular J. So for example, if our K equals to 1 and J equals to 2, we are adapting for output weight 1, 2. Or it can be WO11 and so on. So the point is we are computing this for a particular K and particular J, for a particular weight, output weight. So we have this. Next, we have to compute del Y OK and del over del S OK. So in order to do this, you have to rely on equation 2. So we have to compute the partial derivative of SOK with respect to WOKJ. Sorry, we have to rely on this. We are computing this, so we have to rely on this equation, equation 1. So we have this term after doing the partial derivative, and this can be simplified as this, and this is really YOK multiply 1 minus YOK. So we are done with these two terms. Next we have to compute this. So now we have to refer to this equation. So for a particular K and particular J, del SOK over del WOKJ is just YHJ. YHJ. So putting everything together, you end up with this. So the delta or the changes or the change in our output weight is eta delta OK YHJ plus alpha delta WOKJ, where delta OK is given by YOK multiply 1 minus YOK multiply YDK minus YOK. So there you go. This is the adaptation of output weights. Next, we have to do the same or use the same approach for the adaptation of hidden weights. I don't think I want to go through each step, but basically, again, we have to in order to get the changes in the hidden weights, you have to compute partial derivative of error with respect to the hidden weights, and this can be broken into 3 terms using the chain rule. But because the hidden weights are connected to the output weights, we have some additional terms. For example, if I want to compute del E del SOK, which is here, you would get a vector. So I can explain if you have questions in our discussion later, why do we get a vector? But it's pretty straightforward from your elementary calculus. So the same thing here. When we compute del SOK over del YHJ, you will get a vector. And when you put everything together, you would get this term. So this is the adaptation of hidden weights, or the changes in hidden weights is given by this long term. In summary, these are the adaptation of output weights and bias, even though the derivation did not show the adaptation of output biases. But you can follow the similar approach or derivation to get the equation. And these are the equations for adaptation of hidden weights and hidden biases. So these are the artificial neural network training steps using the backpropagation algorithm. First, we have to obtain a set of training data because we are dealing with a machine learning tool. And remember, the desired output has to be encoded if necessary. So set up the model by determining the following: number of layers, trial and error, input neurons, depending on your data, hidden neurons, trial and error, output neurons, depending on the data, learning rate, trial and error, momentum constant, trial and error, set minimum error. This depends on the specification or the severity of your problem. Initialize all weights and biases to random values. Start training by applying training input one at a time and forward propagate through the layers. Calculate total error. So this is our forward pass. Next, backpropagate error through output and hidden layers, then adapt output weights. Number 6, backpropagate error through hidden layer and input and adapt hidden weights. This is the backward pass. If error is below the error minimum or minimum error, stop training and proceed with model validation. Else, repeat steps 4 to 7. So you have to keep on adapting the weights until the error is below the required error. Now, this is an example of the Xor problem. So we'll be using the backpropagation algorithm to solve a 2-bit Xor problem, which means you have two inputs. The training data is given in the table below. So this is our data. So this is a simplified machine learning problem because you only have 4 data. You don't have any noise in the data, and you don't really have to divide this into training and test data. So this will be your training data, and this also will be your test data. So as shown in figure 1, the neural network has 4 neurons and no biases. So you have 2 input neurons because you have 2 inputs. You have 1 output neuron because you have 1 output. And the number of hidden neurons and hidden layers are really up to you. You can try various approaches. So in this simple example, we assume we have only 1 hidden layer with 1 hidden neuron. The input neurons implement linear activation functions, which is very common, and the hidden and output neurons implement logistic activation functions. So we have logistic activation functions in here and in here. In actual practical implementations, there are various other activation functions that you can use in the hidden and in output neurons. But for our syllabus in multi-layer network, let's just focus on linear and the logistic activation function. The weights are initialized randomly as 0.55 for the hidden weight, WH11, which is this one, and then WH12, which is here, to be 0.15, and the output weight, which is here, to be 0.11. The learning rate and momentum constant have been set to be eta equals to 0.1 and alpha equals to 0.9 respectively. Now, using the backpropagation algorithm, adapt the weights for epoch 1. So remember, you have to know what is iteration and what is epoch. as we have discussed in the previous module. So if you apply these formulas, so all this formula 1 2 3 4 and these ones, so 1 2 3, you would get these values. So I want you to try on your own, and if you get different values, please ask me and we can discuss during our online session. That's all for today or for this video.